me see if I can explain how this works. So let's say we want to know like the average weight of every fish in Lake Michigan. So we're clearly not going to catch every single fish in Lake Michigan, weigh them, and throw them all back. That would be awful. Nobody wants to do that. We can't do that. So what we would start doing is creating, it's called a sampling distribution. So in this situation, we're going to take a sample of, like, let's say 25 fish. I'm just moving this to 25. And, you know, this might be like Bowman's sample. Bowman goes against 25 fish. Those are the weights of the 25 fish. And then down here, we're just going to graph the average of his sample. All right, so he got these 25 fish. I'm kind of ignoring that and just saying, forget all the noise. Just give me the average of your sample. So now Gunner's going to go take another sample. Will he get the same data? Like, he's just going to go out to Lake Michigan, randomly pick up 20 fish. Is he going to get the same data? No. Is he going to get the same mean? Well, I shouldn't say no. He could, right? But probably not. He might or might not get the same mean. So every sample is going to be different. You know, Haley goes to take one. It's going to be different sample, different average. Jessica takes one. Different sample, different average. Those differences are called sampling variability. So let's write that down. The idea that each individual sample is different. I shouldn't say is different. Could be different. So, okay, so Gunner was next, right? So we're going to do Gunner now. Gunner goes to take his sample. He's like 1 fish, 2 fish, 3 fish, 4 fish, counting all the fish. And then he drops down. Like, I don't care about all that, Gunner. Just give me the average. Like, blah, blah, blah. Hurry up. Okay, no, there's your average. So now Haley's going to do it. She's getting hers. I think you get the idea. I'm not going to do, like, individual over and over and over again. But this would be Haley's sample of 25, which is probably different than the first two due to what? Variability. And then I could just kind of fast forward it. And what happens is if you take enough samples, your data becomes normal. And we're going to work with this graph down here. And this is like the idea that an infinite number of people have taken samples of 20 or 25, and we've graphed all of their averages and put them together. This graph is like the average of the averages. And what's interesting, so that's like a, let's define, so go back here, sampling distribution. I wrote down a distribution graph of the average of all possible samples of size n. Does that make sense to you after I showed you what I just showed you? Is there a different way I can word that? So think about like the graph with the bars falling down. We only care about the average. I don't know if that's helpful or if you need to write that or whatever. But so that's one idea, is that a sampling distribution is like, everybody takes their own samples, we blend those together to get an idea of what's really going on. If you have a big enough, we're going to get like qualifications for this, like if you meet this, and this condition, your sampling distribution will eventually be normal, no matter what the shape of the original population is. So I could do like 5 at a time. You can kind of tell if I go to 10,000, 100,000. Like, even though that original, this is like the parent population. This is the, like, what's really happening. Like the fish, most of them are like this weight. You got some giant ones. Even though this is a weirdly shaped or skewed distribution, the sampling distribution comes out approximately normal. So I can put like fit normal, and you can see how it kind of fits right in there. Uniform. If everything's the same and I start taking a bunch of samples, it's going to be approximately normal. It'll let me do custom, where I just kind of put like random, I don't know, something like that. If I start doing a bunch, well, it might take a little longer, but eventually you end up normal. So we will get to the conditions in a second. But questions on that, what I'm showing you there? Okay, let me hop over to my writing thingy. So I want to talk about like what conditions have to be met and how you would So I'm starting to show you like a template. Um, what happens in the second semester is you're going to get like a sample set of data and a claim. Basically, this is like a general idea that like Milo High School claims 60% of its students go to college. And then, okay, well, let's test that. Let's take our sample of whatever, compare our number to theirs, see what the probability of that happening is, and see if we believe their claim or not. So that's kind of where we're headed, and I'm starting to really lead you down that path. The first step in that process is called state or intro. You can call it whatever you want. The first thing you're going to do is you're almost like writing an essay, like a mathematical essay. Where you're like, here's what I'm trying to do. Here's what shows I can do it. Here's me doing it. Here's my conclusion. So the first thing is like state or intro. And we are working with sample proportions to start. We will get into sample means as well. So you would say P equals the true population proportion of whatever. And you would put the context of the problem. So the true population proportion of Milan graduates that do attend college. Whatever it might be. Please don't literally write context. Like every year I get people that literally write that. Like write the word context instead of the actual context. So that's just like a placeholder, right? And then you're going to put whatever you know. So you might know P, probably know P hat, you might know N, and you're just kind of writing down like, here's what we have. And then we're going to do the conditions. And this is making sure that we took our sample properly, that it was big enough, and it was done, yeah. The conditions are represented by, you might want to like watch me write this out first. I'll do it and then I'll give you a chance to write it because that's just kind of the way it's organized. Conditions are R, I, N. R stands for randomness. So you need to have randomness. If you have randomness, that shows that things are unbiased. And that allows you to say that the mean of your sampling distribution of P hats is P. I know you're going with all you're talking. Just write it down. We'll do a couple of little things. Now that I see that, I'm not sure I told you why I told you to wait to write it. So if you're going to take a sample properly, you have to do it randomly. You can't just go to Lake Michigan with our fish example and get the first 20 fishes. Like we talked about different ways to sample. You'd have to technically, it'd be like impossible. You have to number every fish, one to whatever the numbers that catch that fish. Right? It's not going to work. All right, I asked for independence. And there's two ways that that might happen. If you are taking a sample, so like we're talking about taking a sample of fish, a sample of Mile High School students or whatever, you got to make sure that your N is less than or equal to 10% of the capital N. So what I'm using here is little n is my sample size and capital N is my population size. So if I start taking more fish, like if I took half the fish without replacing, now I'm changing the odds and things get a little bit weird. But if I'm only taking 10% of the population or less because I'm not replacing, it's small enough that I'm not changing the odds significantly and I'm allowed to roll with it. Or if you're not taking a sample, you've got to know that each whatever is independent. An example of that might be like you're going to randomly guess on 10 true false questions. I'm not sampling you, but I can say each question is independent. Like one has nothing to do with the previous. Again, I know this is largely like what are you talking about at this point. When we do problems, it'll hopefully make much more sense. If you have those two things, either of those two things, so it's a 4, you don't need both. You are then allowed to say the standard deviation of the sampling distribution of P. That's just all the samples combined. Is, and that's going to be the square root of P then N is for normality. It's called the law of large numbers. What you need to show here is that NP is greater than or equal to 10, and NQ is greater than or equal to 10. Again, I know this is like what you're talking about. We'll make it like more real in a minute. And then I do the math, which at this point is just always going to be a normal CDF. Your low to your high, and you'll tell the calculator the mean, and you'll tell the calculator the standard deviation. That little hat on top of the P means it's from a sample. Have we talked about that this year? Oh, but okay, not this. So this little hat on top means it's from the sample, not from the population. All right, let's do one. That'll make this make a lot more sense. Okay, so let's look at number 2, the University of Michigan one. We're going to kind of use this sheet to work through number 2. U of M claims that 80% of graduates have a job within their major in 6 months. So where we're headed with this is like, well, I think that's BS. I'm going to take some samples and see if I can like mathematically convince you that it's BS. So we're not there yet, but that's where we're going. And maybe it's not BS. We can show that too. So like, the same idea. One of you takes a sample of 100, and we count what percent of people who have a job within their major in 6 months. Another one takes a sample of 100. Someone might get 78%, 83%, 75%, whatever. The idea is we're going to take all of those average, all those numbers, and put them together into one distribution. So what shape is the sampling distribution, and how do you know? If you look at our conditions, the shape we're looking for is it going to be normal? Is our distribution going to be normal? If these two things are true, which we'll check in a second, then the shape is normal. If these two things are not true, you're kind of screwed and you can't really continue, and they don't really present that to you very often because they want you to do the problem, But what shape is the sampling distribution? We're going to check. So what's NP and what's NQ? N is 100. So took a sample of 100. P is 0.8. Initially we believe they're clean. We're like, okay, we'll take your word for it, it's 80%, so P is 0.8, let's roll with that. See what happens. Well, that's 80. That's bigger than 10. And Q, sample size 100. Q is 0.2, so it's probability of failure. That's 20. Also bigger than 10. So what you really, the only thing you really have to write is say NP is greater than or equal to 10, and NQ is greater than or equal to 10, and then you'd say it's normal. So if you can show that, the shape is normal. If you can't show that, you're kind of stuck. That might be a multiple choice. Like, is this normal or not? Why or why not? You could like run through this, and maybe it's too small and you can't do it. But in these logger problems where they want you to like do steps, the conditions are almost always going to be met. Otherwise, you can't do the problem. Okay, what is the center of the sampling distribution, and how do you know? So the center is the mean, and I'm going to say the center is P. The center is going to be 0.8. The middle of our distribution is going to be 0.8. know that because I did see in the problem that they randomly sample. That means it's unbiased. That means everything's going to match up. The center of the sampling distribution, the mean of the sampling distribution, that's what this says. Use mean or center. PI is the sampling distribution. Is going to be 0.8 because randomness is stated. Or you could say because SRS is stated. All right, what is the spread of the sampling distribution? So when I say spread, I mean standard deviation. I'm trying to kind of like guide you to it without telling you, but since it's the first one to do it, I'll just tell you. And how do you know? We'll go back to our conditions. Standard deviation has to do with whether things are independent or not. So if one of these two conditions is met, then we can say, okay, yes, I know this is my standard deviation. So in our situation, we took 100, a sample of 100. Is that less than 10% of all Michigan graduates ever? I would say so, yes. So we're going to write that out. So we're going to say 100 is less than or equal to 0.1 times Michigan graduates. We don't have a number for that. I don't know how many people have graduated from Michigan, but I'm just going to use the words instead because I'm pretty sure 100 is less than 10%. So that like checks the box, and then once I have that, I'm allowed to say, well, the standard deviation is going to be the square root of P Q over N. So again, that's the standard deviation of the sampling distribution for proportion. And then I'm going to plug in my PQ over N. I'll get 0.8, 0.2 over 100. Throw that in my trusty TI-84. So all of that is just like verifying that you have done this correctly, you know it's normal, you know the standard deviation. So basically all of that is to be able to say this. Now I know my distribution is approximately normal with a mean of 0.8 and a standard deviation of 0.04. This is the mean of your sampling distribution, and this is the standard deviation of your sampling distribution. And now I can finally do the math, which is just the regular normal CDF that you've been doing for like most of the year. So 85% or more, I'm going to do normal CDF, 0.85, 9999999. I'm going to tell the calculator the mean, tell the calculator the standard deviation, and I'll get my answer. You do want to convert that 85% into a decimal. Like if you use 0.8 here and 85 here, those are like gigantically far apart. You want them to both be decimals. Some people will say, well, can't I technically just stop at 1 because you can have them 100% or more? In theory, yeah, but sometimes the questions are written properly and it doesn't work. So I just always use 9999 just in case something doesn't quite fit right. So there is a 0.106% chance that if the true answer is 80%, if they're telling us the truth, that 80%, there's a 10% chance that my sample wouldn't show that. It would show like 85% of them. Just because of sampling variability. Like I'm just going to get different things than you, than the next person, than the next person. So the bottom one. Again, it would be normal CDF. What would be my lower bound in this case? -9999. Like technically it's 0, but I think it's safer to use 0.7, and then tell the calculator the mean, tell the calculator the standard deviation. Type that in and see where we end up. I don't really care that much about the answer, but I feel like it's incomplete if I don't do the answer. 6.006. So like what's happening there, our sampling distribution would have a center at 0.8. 0.7 is pretty far away based on our standard deviation, so the probability that we're less than that is going to be really small. The previous question was 0.85. Well, that's not quite as far away as in the middle as 0.7 is. So the area above that's going to be a little bit bigger. This is like all those all the average bars coming down will make this kind of shape. That feels like a lot to me. How'd that go? Are there questions on? I'm gonna have you do one. There's one on the back. Before you do the one on the back, I think I can clear out the dress, clarify. I guess we'll find out. Do the one on the back, and we'll see how it goes. I'll go through them as well. Like I'm not just gonna throw the answers up. I'm gonna talk through each one. Remind me. I think I marked your ass. Okay. Just remind me. Yeah. I was just asking about your group. Are you guys adding those into the second on that? People have how much money?
Yeah. I don't, because like a lot of those like C-SPAN winners have like NCIS.
Yeah.
We just worked on that.
That's way more time.
Yeah. But we'll do our best.
Some people would get like when they have way more time too. Some people just get crazy into it. Like guys come in the weekend. Like they're really going for the more like $1,000 bucks. I think $1,000. This is not the score like that. So that's for AP Gov or Sub? Which one? Gov. How many are in AP Gov? Hold on. Raise your hand if you have a non-iPhone cell phone. Trying to look at like it's 60% too low. That's just my guess. Maybe more. What? It was not a service. Oh yeah, parental controls.
That's
Yeah.
usually
That's why I switched. Like I had an Android up until like last year. All right, what shape is the sampling distribution, and how do you know? So the question basically is this distribution normal or not? So you're going to find NP, which is going to be 300 times 0.6. You're going to find NQ, which is 300 times 0.4. And those are both greater than or equal to 10. So we know that the shape is normal. We just verify that those conditions are met, and we know that the distribution is normal, which allows us to use normal CDF and do all of our math. What is the center? The center is going to be. Ooh, I didn't give you this one, did I? Oh yeah. Okay. The center is going to be 0.6 because it says 60% up here. And what else is the sample there that lets me know that I can use 0.6? It's an SRS. I know that because we took an SRS. You don't have to write this, but what that means is we did it in an unbiased way. All you have to say is SRS. I'm just like adding information. What is the spread of the sampling distribution, and how do you know? I need the things to be independent. So I need to show that 300 is less than or equal to 10% of Americans. I don't know how many people in America. I'm not going to look it up, but I'm fairly confident it's more than 3,000. And then because of that, I can say, well, then I should have written this differently. I should have written the mean of P hat equals 0.6. Same thing. This is like what we're working on. Standard deviation is going to be the square root of PQ over N, which is the square root of 0.6 times 0.4 over 300, which is 0.028. So you guys got it as well? So now I know I have an approximately normal distribution. I know it's normal because of that. I know the mean of it is 0.6 because we use randomness. I know the standard deviation is 0.028 because I know they're independent, and I can just do my regular normal CDF from there. Hello? Yep. Yep. Okay, so 30% or less, I'm going to go normal CDF. Negative 99999 up to 0.3. 30%. Dollar calculator, the mean is 0.6, standard deviation is 0.028. You guys get 0? Yeah. I mean, I think that makes sense. If it's really true that 60% of people have an iPhone, what's the chance that my pretty big sample is going to show 30%? Like that's not going to happen very often. If it's really 60%, then I get 30%. Question on this one. Why did you do this? Where'd you get this from? I got one more for you. So you can do this like in the packet if you still have room there. I thought I had one more for you. Yeah, do that one. estate plan math, you can call it like intro conditions math, or whatever. Tell me what's going on, like P equals this, what's the problem? So just like I did in the notes. Check your conditions, and then do your normal CDF calculation. Can I take the problem down so I can show like my work? Because like how we need from here. If you don't get it, just leave it. This is what I mean. It's kind of like an essay. And then as we get to the next unit, there'll be one more thing at the bottom where we're saying we're basically gonna say we either believe their claim or we don't believe their claim. We're just kind of working our way there, like I said. So this is like your intro where you're stating this is what we're looking for. true population proportion. We're trying to do that with a sample instead of asking every single person, but that's what we're looking for. We know P is 0.6, they told us the problem. We know N is 40 because they told us the problem. And then this is my RIN. I just didn't write the RIN part, but you can. There's nothing wrong with that. So R means randomness. They stated SRS. Because of that, I know the mean is 0.6. I is independence. I am taking a sample, so I look at the sample conditions. 40 is less than 10% of all my MHS graduates, so I know that we have independence, which means I know this is my standard deviation. And then I need to find out the shape of it. Well, since these two things are both greater than or equal to 10, it is approximately normal. And all of that is just to prove, you'll have to write this, but that I have a distribution that is approximately normal, 0.6, 0.077. Like there's three things in that. And I basically showed, verified that we're allowed to use all three. And then if you work out the math at the end, your answer is 0.097. How many had 0.097? Questions on anything on that one? I would like you to do homework 2 in your packet. And you may, because I kind of went off script a little bit off of her like program. I think I do a much better job of this, honestly. But there might be things that you